Maybe we should start.
Yeah, yeah. Okay. Yeah. So fine. So I think, yeah. So based on all the past, what we have done till now, uh, and the end results we are here. I think one of the approaches what Professor Sen discussed, among with others, uh, was part of this particular design concept. But I think Professor Sen did talk about how can we generate new materials, synthesis them automatically, and hopefully validate if the generation has been properly done or not. And one part of it, one part is of course automatic synthesis can be done, and then validation, of course. But then one major component of that is like how can we generate new materials, right? Given a set of properties as prompt, how can we generate new materials? So to do that properly, okay, so generating new materials like which are stable or satisfying properties or not, uh, probably is like a one way. Like you can have some materials which you can just generate and hopefully theoretically they will have properties, but they might not be stable, right? So the idea is to generate not, let's say, a very large number of materials and we have to synthesize all of them. Rather, if we can generate really few and which are absolutely going to make sense in stability and the desired properties, let's say. Yeah, so that would be the one part of this entire automatic synthesis and validation part. Today, like we will just discuss one of the papers, and this also includes one of our work. I have not added slides for our, but I think process and discussed some part of our work that we have done. But this is one of the work that has taken a little bit more in terms of data set size and a little bit bigger. And so the model name is called MatterGen, and this was by I think we have this has come across multiple times. It is by Microsoft Research. This was published in Nature. And yeah, and uh, before this, it's not that things were not there. It's just that this was one of the most comprehensive model that could generate, let's say, new things, and specifically using diffusion to generate 3D crystal structures, right? So there is some form of geometric uh, awareness, let's say, like 3D geometry awareness while generating. And additionally, I told like conditional generation of materials with target properties. That was also kind of new. And how did that translate into finding new materials as such? Okay, so some of things I have written processing, you should correct me wherever I'm going wrong. Uh, yeah. What is the problem? So traditional problem is basically we want to find new problems, and it's like looking for a needle, right? Uh, in a stack of haystack, basically in a haystack. But we are only allowed to look in the haystacks we already know about, right? So we want to find a needle that exists in a haystack of in a haystack that we have no knowledge about. What we have is a group of needles, let's say, right? But we want to find another needle which is a haystack, and we don't know anything about that haystack because those are materials that have been produced and we don't know anything about them, like generated per se. So, uh, so what do we do? So this is like called like computational screening. So we can take a database of known structures, and there are material databases that we have discovered in this course itself, like millions of structures, and then we can do like compute properties on top of them. and either we can run expensive simulations, uh, such as let's say DFT, and then hoping one of them will have property that we want, right? So one of our desired properties, if they have, then sure, and then we will select those candidate, and then we'll synthesize them. Yes. Now the problem is we are limited by the set of materials databases that we have, right? What if the material that we are looking for is not there in the database, right? So what do we do? So this, and also DFT is expensive, and specifically if we want like rare properties, maybe their simulation is rather expensive, or something else exists, or the material itself. The major challenge is, what if the material does not exist in the search space that we're looking for, and satisfying our properties? Then what? That's the problem basically. So given a set of desired properties, can we find a material or even generate a new material, right? So, and this is where basically MatterGen comes into play. This is one of the pictures, a few of the elements that were like predicted, but I will come back to this slide again. Yeah. And what it says is basically, if we do a bunch of earlier works, they either take a lot of time, or uh, probably they produce a lot of false positives or false negatives. Yes. So MatterGen, currently this is the solution that we have, and uh, this is the paradigm shift. Let's say, instead of screening existing materials, we can generate new ones. There were other generating new materials, but this one probably was become a little bit famous because it used diffusion, and other things are there. I'll come back. So what do we do? So here we train a generative model on a stable and valid material database. Yes. And once the model understands, let's say, the grammar of chemistry and physics somehow, that's it, like machine learning. Yes. Then we can ask it to generate entirely new structures, okay, that have never been seen before, specifically conditioned on the desired properties. Now, what are the advantages? Advantages, of course, like we are not limited to the space that we are looking for or searching for. We are gone beyond the materials databases. Yes, and typically going either than looking for each of the sample and checking if they validate our properties. Rather, we have started with the assumption that it has to satisfy our specific design criteria. Yeah. And also the next is, like earlier DFT calculations were taking time. Let's say here, like we are like super fast. Like we can generate materials, or let's say candidates, let's say, that meet the criteria very fast. Fine. Uh, and I think in their paper they show around 100 novel high strength materials compared to just 40 from traditional screening. Fine. So now next, now what do we say? So traditional approaches, looking at the entire database, screening for them properties, and then probably looking at which, but screening properties took time. What we are now saying is we can train a model conditioned on desired properties to generate new materials, right? So now, before we do that, first the model has to understand what are materials. I think some of these parts we have already covered, but I'll just repeat. So, like, first the model itself, which only understand numbers, has to understand materials, right? So, how do we do that? So, one is basically like materials brain. So, we can for the crystal structures, how do we do? So, lattice is there, and give me a minute. To do this, we want to represent materials mathematically. A crystal will be defined by three things. Let's say the lattice, the basis, and the composition. Lattice will be basically what is the repeating box. The basis will be where atoms are inside that box, and the compositions are what are those atoms, right? And we represent these lattice vectors, basically fractional coordinates for positions and atomic numbers for the element types. So we brought down the entire crystal structure to again to back to numbers, but with some structure assigned to it, like letters, basis, composition, and again within that there are vectors and fractional coordinates that follow certain boundaries, let's say, yeah, or range. Fine. Now, even with that ordering, let's say, how do I say, even with that organized structure of representing crystal structures, uh, there are still some issues for the machine learning model to learn, right? At least the standard machine learning models will have an issue. So first is crystal structures are periodic. That means they can repeat in infinitely. But this is not something computers understand by nature, right? Words, sentences, and pictures have an ending, and so on and so forth. And they are also permutation invariant. Like it doesn't matter if you list the atom 1 and then atom 2 or vice versa, right? And then we have a mix of discrete data, like for example, elements and continuous data, which are like positions, right? So now what do we do? So we have to respect some of the properties that come from crystals, matlab crystal structure. So first is we have to respect the symmetries. First, like periodic boundary conditions. So an atom at position x is same as one at x plus a lattice vector, right? So if you're moving from one lattice to another, if the atom is at the same position, so this position plus one lattice distance, let's say, uh, will become the same atom again. So then the second is permutation equivariance. Swapping identical items should not change the physical meaning of the structure, right? Uh, so this is periodic boundary condition, permutation equivariance. Then there is Euclid invariance. So this means like uh, rotating the entire crystal should not change its properties, right? Scalar properties like energy, let's say. So our generative model has to basically satisfy all these symmetries, and outputs must be like physically and chemically valid. Hmm. So this is just a high level overview of, let's say, matter chain. So initially we have a diffusion model. Diffusion we discussed last class. So given a stable material, we start adding noises. But the you have to understand the noise in picture was just adding noise to the pixels. Here noise might be slightly different. We'll come to that. But the same thing, you take a stable material, we start adding noise. Eventually it will lead to a random material. From that random material, we have to go back in the reverse process and we have to reach to stable material. Hmm. And that's the entire process basically. And but there are some other pairs that are attached to it. Specifically, if you see like we have structured data, we have a equivalent score network, we have an adapter to make sure that we fine tune with the desired properties and so on. So moving forward, yeah. So at its core, so basically it's a diffusion model, and it operates on 3D crystal geometry, and it will take the lattice vectors, atom positions, and atom types as input. And in this forward diffusion model, so like forward diffusion process, uh, we add a noise to both the atomic positions and the lattice vectors, so that we gradually are basically what we are doing is we're destroying the structure. And in the reverse process, a neural network will learn to predict and remove that particular noise that we have. Hmm. And all these equations, if you can see, it comes back to the original diffusion equation, right? So here, if you see xt, the same property, I'm not able to select this one, but the same property allows. That means you can predict a noise added material at the timestamp t from x0 directly. Hmm. So those properties from diffusions carry over, but domain specific noise has been added. So some noise added to atomic positions, some noise added to the lattice vectors, which gradually will destroy the structure. Yes, and the reverse will just try to remove that noise, or we either learn the noise and then subtract. Yes. But here, basically, learning noise and subtraction is not there, but rather we reconstruct a valid crystal directly. Hmm. Now there is another part here, basically equivalent graph neural network. Some highlights we have talked about it, and the reason I talked about this in last class because it was useful here. So first is let's go back a little bit recap on what graphs. So in the graphs, basically we can have nodes. So here, for example, we have atoms with features. Yes, and edges will be connecting nearby atoms within cutoff radius, and then periodicity will be like include atoms from across boundary via periodic images. Yes. Now message passing. So I hope you remember. So if one one node is connected to other nodes, in message passing, the information from the neighbors basically is collected by the node in question here, and that is called message. So your message is getting passed from the neighbors to the main. So if you are looking at one particular atom I, let's say, it is receiving messages from the neighbors J. Yes, and where Rij is the relative position, right? And here edges we connect only if it is within the cutoff radius. Fine. And then we come back to the EY, like that is graph neural network or GNNs per se, which do message passing. Equivariant, basically it says that network will output even if we have transformations, like some transformation like rotation or translation. If we have, the scalar features will remain invariant and the vector features will rotate with the input, right? So this is basically the E3 equivariance. And this is specifically useful so that like specifically useful for the material generation, right? So this is physics compliant representation. Now, what was the training data used for MataGen? So around 1,54,000 DFT structures. It was data set is was over 600,000 stable inorganic materials from the materials project and Alexander databases, and specifically unstable was filtered out, invalid structures was filtered out, so that we have good quality set. Yes, sorry, they had a good quality set, and that's basically data filtering part, right? So similarly, I think if when you go ahead and look at the data set, so domain knowledge has been applied, so unstable structures have been removed, large unit cell has been removed, duplicate structure has been removed, and some chemical validation has been performed, so that the total data set that they had using materials plus Alexandria, some filtration was done. Yeah. Now, augmentation, right? So in order to make sure that equivariance property is being maintained, so you have to do some augmentations to make sure the model becomes robust, right? So random rotations was one, and we also basically they also fed the property like bulk modulus and the band gap during training. Basically, this allowed the model to learn the relationship between the structure and the property, right? So you can look at this magnetic moments, formation energy, crystal system, and space group. These were the property labels that were also used. Mm, okay. So the next come is conditional generation. So that means, quick recap. We looked at the stable diffusion process, like let's say, sorry, just the diffusion process. Stable material, some noise was added to the lattice. And the atomic position, and we basically destroyed that to create a random material. From random material we started learning backend to create a stable material. For that, dataset was required. Dataset was produced from materials project and Alexandria. Some filtering was done, and a equivariant graph neural network has been used. I will come back to that. Then conditional generation. So this is the part where again MataGen excelled a little bit. So here basically what they want to say is they don't want to generate random crystals. They might be stable, but that's not useful. Rather, they want to condition it on a particular property. Right. So here they can give a prompt like give me a material with bulk modulus greater than 4,000 GPa, let's say, or 400 GPa, sorry. Or it can be on a composition like give me a structure with lithium, cobalt, and oxygen. Right? So either we can do a property conditioning or we can do a composition condition. There is also another condition that we can use is called crystal system. So we can specify the symmetry, either it can be cubic or hexagonal. These conditions will be embedded and fed into the network by cross attention mechanism. Attention we talked about earlier. Quite attention is assume it's a dot product of two vectors, right? If the dot products of two vectors belong to the same domain, let's say, then it is like it's the same domain. Let's say, like generally it's self attention or just attention. If it is comes from a different domain, then it becomes a cross attention. Uh, Fine. Okay. Now, this is again something that we touched upon last class as well. So, like there was a place where we wanted to do a classifier free guidance for the materials. Uh, give me- so, what will happen here is if I start doing conditioning for any model, let's say, I will give the condition, let's say in the beginning, or let's say at the end, or in the middle, somewhere I have to give the condition. But if I have a classifier that is attached to it, what will happen is generally classifier included guidance, let's say classifier based guidance models. You generally, what you'll do is you start from a random material. Mattergen will generate new materials. And then there will be a classifier setting at the end, which will basically classify if it follows desired properties or not. But if we do this kind of things, then the problem is basically Mattergen as a whole has already invested a lot of inference energy per se, GPUs, let's say, to create materials which might not be useful and classifier might finally reject it. To not to go ahead with that kind of heavy load of pipeline, let's say, what you can do is you can do with away with classify free guidance. Yes. So this is basically you're trying to train the diffusion model itself to be conditional. Hmm. Uh, yeah. So here, what we do is we basically train the model both with and without conditions. Right? So to do make it a classifier free, what we can do is first we train with and then we train without. And then while we do sampling, the actual inference, let's say, process, we will push the model towards conditional prediction. So we train the model both on with and without condition. And then at the final end, what we'll say, okay, then we will just keep on asking about the conditional prediction. So the final fine tuning will be on the condition. So here, let me see. Oh yeah. So like yeah. So here a guidance weight is being used. This is similar to the previous lecture. I did not go through a little bit detail on that, but uh, we'll explain here. So if you use something called a guidance weight, it's just a parameter that controls how much to adhere to the condition. So and then if W is high, then we force the model to pay lots of attention to the constraints, right? And this will dramatically increase the success rate of generating materials with the desired properties. Yes. And if we say just W is equal to 0, there will be no condition, and 1 is just probably, yeah. But stronger conditioning, you have to increase the value of W. And W sits here basically in the same loss function. And this is the on W is applied on the conditional diffusion. Hmm. Okay, fine. Now, so we use the matter chain using, sorry, first diffusion, how to train, and then conditioning. The next thing that comes is basically another challenge that exists is called compositional disorder. Hmm. Sometimes what will happen, a specific site in a crystal will be randomly occupied either let's say iron or cobalt, let's say. Hmm. This randomness will be it's very hard to represent or evaluate. Yes. Uh, but you can probably feel it more than me. So I'm just saying I can understand the terms. Okay, there's a random anomaly in the material structure. Let's say. So that particular structure, sometimes iron comes, sometimes cobalt comes. Let's say. So now, how do we do this, right? So it becomes a challenge for evaluation, and traditional structure matching basically fails. Uh, okay, and so like there are two generated structures now. Like if for that particular material, let's say if he is at like site one, iron is cobalt at site two, and then cobalt at site one, and if he is site two. Now, are these different or the same? If we go by traditional method, they are different atomic positions. In reality, they are the same. Because you can like stop me if I'm going wrong on materials part. Uh, so reality will be they are the same thing. Yes. But still, if we go through traditional methods to evaluate this, if the generation has been correct or not, that will give a wrong answer, right? So next, hmm. Now, like what did material gen then introduce to handle this compositional disorder? So so it introduced a bunch of things, but the algorithm goes like this. Uh, Yeah. So basically, it introduced structure matching algorithm, right? So first is the symmetry analysis. It will identify the space group and the weak of positions, and then it will do the site equivalence, like determine which sites are symmetrical equivalent, and then it will do a composition matching. That means if I do permutation on equivalent sites, if it's still the same, and then distance calculation, you compute the structural similarity accounting for the disorder. Right. So this is the algorithm that they introduced. This is new from their point of view. Um, so it basically uses symmetry analysis to identify equivalent sites and checks if like the atoms are just permuted versions of the same disordered arrangement, right? And mathematically, it will just check whatever the rules you have. It will just check if for equivalence by searching for a rotation or permutation, right? Rotation and permutation, sorry, and that will map one structure to the another, and it will respect the site symmetry. Right? This will ensure that we don't overcount the duplicates. Hmm. Hopefully, this will then it will improve how much novel we are. Otherwise, it will think that it is probably two different things and just try to give random numbers, like how many novel materials it could generate. Fine. So then the next is basically once we have architecture is fixed, we have used let's say diffusion, equivalent networks, and then conditional stuff, and then we have used the structure matching algorithm, and then finally let's say we begin to learn, right? So then we start with our loss function. So the training objective is basically a combination of a bunch of terms. So the main one is basically, if you look at this, the first one, let's say, it is majorly we're trying to look at is the diffusion loss. It's basically predicts how much noise has been added and can we remove those noise. But there are some auxiliary noise that are added to penalize the invariant structures, specifically like atoms that are overlapping and basically to increase the symmetry. Hmm. So this is basically the validity and the symmetry. And then lambda 1 and lambda 2 are basically our choices, hyperparameters on how much we value them. If you put really high on like validity and symmetry, it might end up in producing nothing because there is a true restrictive thing. So some relaxation has to be done. Like it cannot be super valid and super symmetric. That's fine. And next is the sampling process, of course. Like so, sampling process is the like inference process, fine. So what you do is you start from a random noise xt, and there you iteratively you keep on applying the same matter gen. Basically it will start removing stuff. Hmm. And then you output the new crystal structure that has the original three, right? So that is atomic positions and atomic numbers. So and then you have to do a little bit of post processing. So post processing will basically involve you want to do the symmetry, you want to like how to symmetrizing, let's say, the output to the nearest space group, and we'll run a quick DFT relaxation to fine tune the geometry. Right? Then they check for basically stability and they calculate the properties. So symmetry relaxation, you run a little bit of DFT to make sure geometrically it is right. Then you do a stability check. Then you do property calculation. Now, how do you evaluate? At the end of this, now you train the model with a loss function. You do a sampling to generate new materials. Then you do some kind of post processing to make sure things are in order. Now, how do you make sure that the whatever you generated is correct or wrong? Because this has to be still automated, right? Otherwise, it will generate 1 million. You cannot sit and verify 1 million of those. So, how do they do? So, they do three like multiple ways. So one of them is structural validity. So there will no atom overlaps and reasonable bond lengths. Hmm. and charge neutrality. If the overall structure is electrically neutral, then composition validity if it matches the specified formula that if we have given so, and then this because we want material that could actually exist, right? So stability has to be also checked. Now, even and a few others. So basically, novelty is another metric. So we what they do is basically they whatever they generate, they match against the original, let's say, materials project and let's say another database ICSD, and they use a structure matching algorithm. If there is no match between what they generated, let's say, versus what exists, then that is novel. Yeah. And yeah. So, and the next is like property accuracy. So here they basically check, okay, so now we have generated new materials, we have post-processed it, we have evaluated if it is okay, then we have also checked if it is novel. Now we just to make sure that because we added some condition on these properties to be satisfied, we also calculate property accuracy. That means whatever materials we generated are basically satisfying the properties that we initially wanted them. Hmm. This is like very similar to like accuracy that we have. It's basically samples that meet the target by valid and stable samples. Hmm. This is half. I thought this was half like a half measure because they could generate a lot of invalid and unstable samples, but the success rate they are calculating is using this, like the samples that are meeting the target by what are the valid and stable samples they produce. So now just to give a highlight on the results, so they have like if you initial if they do unconditional generation, the data set will be like 600,000 materials, the earlier data set, and if you can see, the matter gen starts generating like 89.3% they are valid, 52 are stable, novel will be 94.6, and then unique is 97.2. Yes, and any the previous baseline was doing low, let's say. Hmm. and and if this is still for unconditional, that means there is no property that is given. Yes, and analysis basically most generated structures will be chemically reasonable, good stability because at least half of them at least go through DFT stability, and definitely highly novel because 94% don't even exist in the training criteria in the 600 materials, and uniqueness because it will generate every whatever you generate, you can generate 100 copies of one material, right? So here it basically calculates all the materials that is generated are basically unique, they don't have similar structure. So they basically end the first part of the paper here, right? So, and they wanted to showcase one strength. So, what if we wanted to find very high strength materials, right? So, now the conditioning starts, right? So, the task is to generate materials with bulk modulus, let's say greater than 400 GP. Now, they initially they yeah, screened millions of known materials. They found around 40 candidates, and then basically it saturates. Let's say there is nothing more in the database. Now, what did MatterGen achieve? MatterGen basically generated 1,000 structures conditioned on K is greater than this one, and they eventually had like 100 plus novel materials. Yes, and these are completely new. These are not in the database itself. So, and then so that's a like very nice thing. So almost like 2.5 times more than the screening. And some of the things that they were able to do is uh, like new diamond-like carbon phases, novel boron nitride polymorphs, transition metal carbides and nitrides. Uh, and if you can look at this, so what they're winning, where they're winning is basically they're saying that we just ran through GPUs and just did some validation, which is around $1,000, but equivalent screening would cost 10,000 and plus. And even if you spend that much money, you would still not be able to find more than 40 where they could generate 100. Hmm. Fine. It's not that they ended paper just with theoretical thing that, okay, we have a model that could generate. They landed up basically at least collaborating with the experimentalist basically in the real world, let's say, to actually synthesize a predicted material. Right? Uh, so here they wanted to target, let's say, bulk modulus of 150 to 200 GPa, so for synthesis feasibility basically. So what did Matagen do? It produced, let's say, okay, I'm probably not the best person to like pronounce that structure. But then once that they produced this particular structure, DFT calculated its like bulk modulus, and then uh, it was synthesized, high pressure, high temperature synthesis, characterization was done, then finally measurement was also done, and they say, okay, so whatever we predicted, it's very close from an experimental perspective. That's what was the final defining criteria, that this like the first of a kind experiment which eventually like machine learning was able to produce a new material. So, and this part is what made the paper very strong, right? So, they were the first to basically experimentally validate AI generated inorganic material. This confirmed that, okay, like through diffusion, equivalent networks, and conditioning, and how do I say, and post processing some parts of it, and training on like large databases, eventually can actually produce synthesizable materials. Right? And then property predictions were very accurate, around 8.6% different, but that's okay. Uh, so challenges overcome, like basically high precision synthesis not required, novel composition, and crystal structure determination. Right. So all this was a challenge earlier. Now no. Yeah. So DFT theory says 185, experiment says 186, 169. Very nice. Yes. Fine. Now, just a few examples we'll go through. So, this is what they used also. So, input is like generate lithium containing battery materials. So, output was novel lithium metal oxides and phosphates. This was the output from Atagen itself. Yes. And then, for example, property conditioning they had. So, like band gap is equal to this particular range for solar cells, let's say, and outputs will be like semiconductors with target band gap. Yeah. Excellent. And then multi-property, let's say we want to infuse two properties at the same time, let's say high bulk modulus and low density for aerospace applications. And output is basically light and strong materials. Right. So, and it continues. So we can do even more. So we can generate like battery materials with lithium, solar cell materials with specific band gaps, and then we can also optimize for multiple properties, strong and light. Yes, and crystal system as well, cubic symmetry, magnetic, so cubic ferromagnets. And the success rate, if you can see, like single property is like, of course, like 60 to 80%, but if you infuse multi properties, 30 to 50%, but it's still good, right? Uh, Now, like screening versus generation again, like screening will be limited by the database itself. You cannot go beyond the space that you have. Eventually, like you will run out of that, right? So, but here in generative approach, you just need to train it, learn distribution of stable properties. You generate conditioned on properties. You will eventually have novel candidates. The idea is you will have unlimited, and the idea is basically whatever new novel candidates that you can actually synthesize that can go back to the training set. Yes. So the more training, more synthesis, and more final will produce more training data set that can go back, feed into. So it forms like a loop, right? Uh, Fine. And this was again another table that basically justifies why they're good, and of course, like they can do stuff. Okay. So what will be advantage? So earlier models, I think we have also discussed. Another thing is variational autoencoders. So previously, variational autoencoders were used. Hmm. And diffusion actually beat variational autoencoders earlier in images, but this was kind of first application of diffusion for generating new materials, right? So here again another proof that okay, diffusion can beat in generation compared to VAs. And second is basically they added this equivalence property so that the crystal geometry is at least preserved, and conditioning of the targeted material. That means you can add multiple properties even. Yes. And then finally, you can have structure matching algorithm specifically for the compositional problem. Okay. Just a quick note then. Um, so here for the equivalent layers, so rotations and reflections should not change predictions. So they have something called equivalent message passing. So here instead of just adding, like just doing a summation, they specifically use spherical harmonics to encode the angular information, and then uh, it makes it to be rotationally consistent. Again, this is a little bit advanced topic, but we're just discussing. And so first step is to make sure that the message itself is updated with, even if there is a rotation, it does not affect the eventual message. And now when the node up has to be updated, uh, they use a sorry, so when the node has to be updated, you aggregate the messages from the neighbors, but still you maintain the crucial geometric consistency throughout the network, right? Uh, so even if let's say the input rotates by r, the output also rotates by r, okay, and vectors or stays the same, yes, if it is scaling. Now, how did they implement? Just a brief overview. So, uh, uh, yeah, so the model itself was around six message passing layers. The neural network actually have seen like the layers of nodes, and there are six, but message passing is something like how many times you ask your neighbor to give your information. Because every time you ask your neighbor to give information, your neighbor also starts getting information from its neighbors, right? So if you do six times, that means technically you are dragging information from the sixth hop. That means neighbors that are six edges away, you are taking that information in. Yes. So six message passing layers. Dimension is like hidden dimension will be 256. Cutoff radius is where you put an edge or you don't put an edge, 6 angstrom. Spherical harmonics that was discussed in the previous, so 3, and time steps is 1000 for the diffusion, right? So how many time steps you will add noise, and the scheduling is basically cosine. And so here optimizer is Adam. I think we did talk about Adam earlier. And learning rate 10 to the power minus 4 with cosine decay. Batch size will be 32. GPUs is 8 into A 100, and training time is 1 week. Yes, and total number of parameters is 100 billion. Yes. Uh, uh, just to give a hint note, so diffusion models technically are not that bigger. Hmm. And the method was like DDIM. I hope you remember last class. So when we did DDIM, I told like the DDPM was the denoising diffusion probabilistic model, that was the earlier one. DDIM was done so that this diffusion process itself or the sampling process itself can be done quicker. Instead of going again 1000 steps, we can do it with 100 steps also. So it can be like 10 times faster. Now guidance weight is there. How much property has to be taken into importance? They use 3, and then time per sample was around 10 seconds on GPU. To generate one material was 10 seconds. Excellent. So, and just to give a like a slight there is actually Microsoft has another tool, Matter Sim. So they wanted something that complements. Matter Gen basically they generate novel structures. Matter Sim they had another software which basically predicted properties fast, and then it filtered, and then DFT basically validated the refined set. Fine. And this is also open to try. This code is on the GitHub. Model weights are available on Hugging Face. So, for example, even if you had the code and nobody gave you weights, you have to still train it. And sometimes the training process, when they say this one is this easy, you just set up this and then do this. A lot of work goes into this. The 1 week training time that comes at the cost of like probably 1 month or 2 months of trying how to train. Hmm. So, Hugging Face is there, training data materials for Alexandria. Like typically the idea would be like whatever you new generate, if there are other data sets, you keep on adding, make the model better. Yes. So in Hugging Face, you can have pre-trained material generation model, and you will have the training script and configuration specifically if you want to add a more, and then sampling and generation code, structure matching algorithm is there, and tutorial and examples will be there on the same GitHub page. So if you just search for MataGen Microsoft on the web, it will happen. They also provide directly like a library. So here, if you look at just you write from MataGen, if you write and you just import the model and you just give them the condition, number of samples, how many number of samples you want to generate, what is the condition, and what is the temperature, let's say. This is not the material, this is something else from ML side, but 1.0. If you give this, it will start generating a structure for you. And now, what are the applications of this? Finally, if you have this, so energy storage is one, like battery materials and hydrogen storage materials, and electronics also, like semiconductors with specific band gaps, transparent conductors, thermoelectronics, and also structural materials. I don't have to tell why materials are important. All of you joined this course because of that. But you can see the applications, right? So specific, we can earlier was like finding this screening materials in the limited scope of database library that we have, or otherwise now we just tell what properties we require for this particular application and we generate stuff. So now, okay, so if everything is good, then research would have stopped in material synthesis, like at least AI driven. But there will be some issues. One of them, like we'll discuss few of them. One is synthesis feasibility. So sometimes, so in the database project, at least we know whatever there in the materials database, we at least know they are stable and you can produce them. Somebody has written exact way to how to produce. But here, if you synthesize, like even if it is 50%, let's say good, rest of the 50%, if we go ahead and okay, we are happy that we got a material, but it might be very difficult to synthesize itself, right? And maybe they require very high pressure and high temperature, right? So, and then property accuracy, like DFT itself might have 10% errors. So, even if it is 10% away itself, DFT might have 10% away itself, then you are far away, right? And then some properties like ionic conductivity and others, which you might know, might be even harder to predict. And this has been only trained on inorganic materials. So, then we are limited to that scope. Then also the scale also. More than 100 atoms, it will be still challenging. And then molecular crystals will be less represented in the current data set as well. So, yeah. And uh, and probably more property ranges has to be done experimented. So what you can do is basically, as I was telling, active learning, one of them. So you generate, you test, and then again you retrain. You add those new materials that you generated, which are stable and you could synthesize back into the tool. Fine. Uh, and then synthesis prediction, hopefully like while you are generating this, can you add a property like can it be synthesized? Yes, that would help. And probably like you could use GNN and DFT together to make sure it is probably faster to do some uh, all those property prediction that we do can it be made faster. And some of the long terms are, of course, like can we expand to organic materials, right? So, and then can we generate materials with specific defects, right? Doping and alloying, those are like very hard to do problem, not right now. And jointly optimize material and synthesis route. I think Professor Sen talked about in his last class. So, can we jointly optimize the material and the synthesis route and do the automatic synthesis all together in one pipeline? So just to make sure that it's not only materials where things are getting done, AlphaFold is the equivalence of that in the protein folding place, where it can predict the 3D structure. But with prediction also it can generate new proteins. Generally, new drug discovery is one of the targets here. And specifically RF diffusion protein design, it will generate new novel proteins with target functions that are there. So, and this diffusion model is like modeled on the protein backbones. Yes. As you can understand, like diffusion is great at generating this one, valid 3D structures, and that valid 3D structures come from this equivalent neural networks that we have discussed in the matter gen itself. Hmm. Uh, so yeah, so like these are all like the like future slides, but I hope you understand like everything that was slow and the database was limited. This opened up the entire path. There are some ethical concerns, like if you can generate whatever materials, uh, then you could generate materials for weapons, and then somebody needs to protect the output of MatterGen, right? If MatterGen is free and somebody starts questioning like how can I generate harmful materials, then what do we do? Some data bias might be there, like what if there are some materials that we have in our Indian community that are not available in the database, what do we do? Like that, if that can go into the pipeline, then AI training itself has some carbon footprint which you don't calculate. So yeah, okay. And the other things are basically who will own AI generated materials. Let's say today we ran a thing and somehow what did we, even if we did not synthesize or did not do anything, just ran MatterGen and it somehow produced. Can we patent it? Yes. Uh, so that is another intellectual property, or it goes back to Microsoft because Microsoft prepared MatterGen. Or it was our clever prompt that made it produce. Yeah, so there are a lot of people involved in this producing the new material generation, and also like accuracy is still far off. It's produced 100 maybe among 1 million of others, and I told you about their success rate calculation. It was success over valid and stable materials, which they screen out after, like after generating. They do the post processing to find out stable and valid materials, and then they calculate the success rate based on that. And this one I'm ignoring for right now, but overall this, yes. Okay, so that covers a brief overview of MatterGen. If I hope, like, this is again advanced topic. I just want to understand like where it is, but this was again in like earlier this year. So I think, and the work must have happened in the previous year. So 1.5 years has gone by since, let's say, MatterGen work at least has started. So we don't know what 1.5 years will have eventually given rise to. So we'll wait for something new that will happen in material synthesis. Okay, with that I end. The slides I have added to the thing. So if you want to follow, please follow. Yeah. If there are any other questions, please let me know. And this I've given you, and this slide, because the slides are up, maybe you can try MatterGen also locally in your thing, if it just for fun as well as for trying also. Yeah.
Yeah, if I can have a couple of minutes,
Yes.
I will, I had prepared a comparison, so this may be of interest. Let me try to share this. Uh, Along with some details, I had this slide just to show, just to sort of highlight that recently, I mean, it is not as big or as complicated a model as MatterGen is, but we developed a model based on diffusion, which just uses these IRCR representation that I have discussed in some of the previous lectures. So I'll quickly tell you where it differs from MatterGen. See if I can find out that particular slide. Yeah, so this is what MatterGen does. I mean, it has been already discussed that how it represents materials. You have atom identities, you have lattice, and you have their coordinates inside the unit cell. But this is the important part. So it's a diffusion model, but different parts of the material's representation, A, L, and X, they undergo separate diffusion processes because these are inherently sort of slightly different quantities. A you can represent by numbers, the atomic identities you can represent by atomic numbers. L just vectors, and X are fractional coordinates, but they have this inherent periodicity. So these are treated separately. But what is done in this model is this entire thing, this entire matrix, 2D matrix, if you wish, IRCR, is represented, is treated as an image, and then it's like it's similar to like adding noise to the picture of a dog or a cat. The whole thing is sort of made noisy and then denoised again to recover the original thing. And once you have mastered that process, you can generate new materials. And so I'll just do some quick comparison. Uh, so how complicated the model is, that determines what the training time would be. Mattergen, of course, is a very complex, very powerful model, but it has 46.8 million trainable parameters. There are a couple of earlier models, DeepCS and DeepCSP++. These had 12 million parameters. Chameleon had 13.8. In comparison, because of this simple architecture, simple idea that the whole thing is uh, sort of diffusion happens, there's a single diffusion that happens. So there is one spore function that you have to estimate. So there is only one neural network. So number of parameters is also much less, and it is only 1.3. So what that does is it number one, it cuts down the number of the resources that you need for training, and it just took us 17 hours on a single H100 GPU for training. And then the real difference comes in how quickly it can generate new materials. So whereas that number is not available for Mattergen and Chameleon, but for Deep CSP and CSP, this is of the order of 1 to 2 or 1 to 3 materials per second. Okay, 1.25 materials per second, 2.77 materials per second, whereas Diff Christian can generate 308 materials per second. So that's the kind of difference it makes. On the other hand, there is a cost also that unlike Mattergen, it cannot generate structures very close to the optimum structure. Uh, One requires larger post-processing computing, but the generation process is pretty fast. So this is also, the reference is here. So Shubhankar and I and our students, they were all involved in this. So you can also check this out. There is a GitHub page related to this, which you can access and try this model if you are interested. So that's it. I will not get into further technicalities of this, and I'll just stop here. And I can share this also.
I think this with this query we're ending the course as such, including advanced query.
Yeah. So maybe next week, what do we do next week? If there is a discussion required before the final presentation, we can meet and try to clear out any doubts they may have one of these days, Monday or Wednesday. And then we'll have the presentation on, at least Shulagna's group, they wrote that they want to have the presentation on Friday, the 12th. That's fine.
Yeah.
Okay, then.
Okay. Fine. Yeah. So, like, just to tell, like, if any other people are also joining, other people, though, we have asked you to submit their assignments if they want. And Sulagna, if you want, you can just email us if Monday is a good time, then really we can join and have the
Yeah, we can
discussion tutorial.
have the
Yes.
discussion on
Yeah.
Monday.
or otherwise Wednesday, and then Friday we can have the
Yeah.
test. Yeah. Okay. Okay. Thanks a lot.